In this video, we'll look at some more practice with these types of reactions and predicting their products. If you had a chance to try a few of these ahead of time, I think that's helpful, because then all you got to do is check and see if you're getting the answer right. If you are, fast forward the video. If you didn't get it right, then you'll see where you made your mistakes. Number 9 should be a synthesis. Sodium metal is reacted with chlorine gas in a closed container. So if we only have two elements, there's nothing else we could do but join them and make a compound. The sodium metal is a solid, the chlorine is a gas, diatomic, and then if there's no water present, the sodium chloride will be formed as a solid. I'll show you this reaction in class. Water is aqueous, but that's if water is present. In this case, we don't have any water present, so the sodium chloride will be solid. We're going to look at a lot of these reactions in class so that we can write the equation on paper and then look at what's really formed to see if they jive. Is what I predicted on paper what I really experience if I run this reaction? I love number 10, the decomposition of hydrogen peroxide. Liquid hydrogen peroxide breaks down to form liquid water and oxygen gas. This is an endothermic reaction. Energy is required to break bonds, which is why hydrogen peroxide is often stored in those brown bottles. It's just ultraviolet light. Energy from the surrounding air is enough to decompose your hydrogen peroxide. So over time, if you had a really old sample, it could be a lot of water. The liquid hydrogen peroxide and water are naturally occurring. Otherwise, you don't use that L liquid as a phase symbol very often. 11 is another endothermic decomposition. We're going to run this one together in the lab. We're going to take some solid potassium chlorate. It's kind of a white solid. We're going to heat it with a Bunsen burner, and we'll produce potassium chloride and oxygen gas. And again, the potassium chloride, if you look at a solubility chart, it would say aqueous, but that's if water was present. And in this case, there will be no water present, so it'll be formed as a solid. Then we just have to balance this, and again, we can't balance by changing any of the subscripts. So the only way I can balance those 3 oxygen on the reactant side with 2 oxygen on the product side is to look for a common multiple. So in this case, we'll go for 6. Is a combustion. Sugar burns in the presence of oxygen. Sugar is an organic compound. It's burning in oxygen. So my products are carbon dioxide and water vapor. We mentioned that combustions are exothermic. Energy is released. So often that water is in the form of water vapor. We're going to run that one in the lab. Super cool. Looks like it could be boring, but it's going to be awesome. Burn some sugar. 13 is a synthesis. Water reacts with carbon dioxide to produce carbonic acid or hydrogen carbonate. Here's a synthesis where I have 2 small compounds joining to form one product, one larger compound. Now we'll run this one as well. Water is a liquid. We're going to bubble in some carbon dioxide, and we should form carbonic acid or hydrogen carbonate. This is all balanced. It's great. The carbonic acid is aqueous. It will dissolve in water because there is water present, and we should be able to test the pH and make sure that our product is acidic. 14. Awesome reaction. These things look kind of boring on paper, but I promise this is super cool. We're going to eventually run this one in the lab too. Not for a little while, maybe after spring break, but we will run this. We're going to take iron 3 oxide, which is really just rust, and it is a solid. We're going to react it with some aluminum metal, another solid. What's cool about this reaction is that it's highly exothermic. It's amazing. It's supposed to be kind of an outdoor toy reaction. The day we run it, we'll have to see the weather conditions. If weather's not appropriate, we may run it in the lab. We'll get crazy. Highly exothermic. A single replacement where the aluminum is positive, so it'll switch with the other positive iron. If I check my reactivity series, I have to make sure that aluminum is more reactive than the one it wants to switch with. So in this case, the aluminum must be more reactive than iron. And it is. Now again, it doesn't matter what order you write these things in. I can put aluminum first, I can put aluminum second, but the aluminum that's positive would like to switch with the other positive. And that would be the iron. So we'll form aluminum oxide, and my other product will be the iron. Now when we run this in the lab, there is enough energy released that sometimes you can form molten liquid iron. Unbelievable. Now how would you know that without running the lab? If you put solid, because normally iron is a solid metal, I'd be totally fine with that. A couple more single replacements. Magnesium metal is added to a solution of copper 2 nitrate. The magnesium is normally a positive ion. The copper plus 2 is obviously positive. So the magnesium needs to be higher or more reactive than copper. And if you check your reactivity series, it is. So we'll switch the two, and then this one's a piece of cake. If they happen to have the same charge, you're not going to have to balance this thing. We'll kick out copper, we'll form solid copper, and a solution of magnesium nitrate. The magnesium nitrate is aqueous because there is water present. The original copper nitrate solution contains water. So if magnesium nitrate is soluble, it will dissolve in the water present. 16 is one of those single replacements with water. They're kind of a special situation. So make note of these. Put a little star by something like this one. We mentioned that when you use water in a single replacement, write water as hydrogen hydroxide. The positive lithium will only switch with one hydrogen. And lithium is more reactive than hydrogen if I check my reactivity series. So we'll kick out the hydrogen, we'll form hydrogen gas, but then lithium will come in and bond with hydroxide. You'll form lithium hydroxide, which if you test this in the lab, it's a base. We're going to run a couple of these in the lab. If a metal reacts with water, you'll always get bubbles of hydrogen gas, and the other product will be the metal hydroxide. And we can test it in the lab to prove that it's a base. It's aqueous if I check my solubility chart. Most hydroxides do not dissolve, but lithium hydroxide will. And then all I have to do is balance it. Awesome. Hopefully these are starting to catch on, right? Number 17 is a synthesis. Hydrogen gas reacts with chlorine gas. So what else are you going to do but join the hydrogen and the chlorine? We'll produce some HCl, which is a gas. Don't get your undies in a bundle about some of these phase symbols. Maybe on a test or quiz they would hint at that and say like to form a gaseous product or something like that. The solubility chart really only helps if your product is either aqueous or solid. So often a gas needs to either be something that you're familiar with or they'll give you a little hint. And finally, the last crew. Number 18 is a single replacement, but it doesn't work. An iron nail can be placed in a solution of sodium chloride for hours and hours and days, and nothing happens. The iron is always positive. It's a transition metal. They have multiple charges. Its most common charge is +3, which again, that would probably be given to you on a test or quiz or in the lab. The most important thing to know is that it's positive. So the iron would like to switch with sodium, and according to the reactivity series, that cannot happen. Iron is less reactive than sodium. If you get good enough that you can tell just by looking at the original sentence, you don't have to write formulas. You can just tell me no reaction. 18 is the combustion of butane gas. They give me the formula for butane, C4H10. It's burned in the presence of oxygen. So my products of a combustion are always carbon dioxide and water. Exothermic, so the water is often water vapor. And then we just have to balance this one, making sure that all atoms have the same number on both sides. Sometimes this one gets a little bit tricky. Your first gut instinct is maybe to put a 4 in front of the carbon and maybe a 5 in front of the hydrogen. 5 times 2 would be 10. But then you'd end up with 5, and this would be like 8 oxygen, and you can only use even numbers of oxygen on the reactant side. So anytime one side is even, one side is odd, find that oddball and double it. So then I doubled this so that it was 8 carbon, 10 hydrogen, 10 times 2 I should say, for 20. Which then if I double my original butane, I could get this to work. There would be a total of 26 oxygen on both sides. 13 times 2, and then here's 16 and another 10. And finally, number 20 is a double replacement. Solutions of sodium hydroxide and copper 2 sulfate are combined. The rule with a double replacement is that my reactants must be aqueous. So we check our solubility chart. All sodium compounds are soluble in water. Most sulfates are also soluble. There are a few that don't dissolve, but copper is not one of the exceptions. So this is a go. If even one of these reactants would have been solid, this would have been a no reaction. They both must be aqueous, meaning that they're both willing to let go of their current partner and make a new combination of products. You can either switch the positive sodium and the positive copper, or you could switch the negative hydroxide and the negative sulfate. It doesn't matter what order you write your products. But I do need to be very careful with my charges. When I make a new combination of ions, you got to watch those charges. Copper with hydroxide is now plus 2 minus 1, so I need a little 2 there. Sodium with sulfate is a plus 1 minus 2, so I'm going to need 2 sodium. This thing balances really easy. I just need 2 sodium hydroxide. And then finally we finish off the phase symbols for our products. Most hydroxides are solids. There are a few that dissolve, but copper hydroxide is not one of them. That one's a precipitate. If I were to run this in the lab, I should get kind of a cloudy solid. If I run it through some filter paper, that copper hydroxide would collect on the filter paper. The solution that drips into my flask would be the sodium sulfate. Anything with sodium is aqueous. And again, most sulfates are aqueous. There are a few that don't dissolve, but sodium is definitely not one of them.